Good morning, everyone. I am really grateful to the organizer for having invited me to this great meeting. This is not the first time I talk about general patterns of plant specialization, but the really good thing about being in such a specialized meeting and in day 2 rather than day 1 is that I can skip a number of introductory bits. For example, I don't have to talk about what a trait is, or whether trying to find general patterns of specialization makes any sense at all. If you are not just vaguely aware of this, you're probably on the wrong meeting. So instead, I'm going to use this extra time to describe a bit how this very complex landscape of people looking for general patterns of plant specialization is, what are the different trends, and where we put our own work within that landscape. And to describe that, I need to use a metaphor. If you imagine all the various species working together in ecosystems around the Earth as a fabric, something we could call the fabric of life, you can think of the fabric as having 2 components, as any fabric does. And the main components are the weft and the warp. The weft is the outside aspects of the fabric. It's full of color and full of texture, is the most appealing one. And on the other hand, the warp has a number of more uniform and coarser and duller threads, but without those threads, the whole fabric would unravel. And this, in a way, illustrates 2 very different ways of doing ecology, including plant trait ecology. Most of the published work, and increasingly so, is about the weft. It's about the exquisite ways in which plants are different from each other, the exquisite ways in which plants find very, very slightly different ways to coexist and to respond to the biotic and abiotic environment. This is the legacy of the naturalists. This is the territory of ecological splitters, if you want. On the other hand, there's much less literature on the warp aspects, about the really fundamental patterns in which plants are all the same, very different, the ways in which plants tend not to differ. And this warp territory is the territory of ecological lumpers. And most of my talk today is going to be focused on the lumping aspect of ecology. And ecological lumping has a long tradition. We can trace it back all the way to Theophrastus. You probably know he lived in ancient Greece. Some people think he looked like that. And he was interested in finding very general ways of being a plant. Now, he had a simple mind. He wasn't very fond of nuances. He would say, look, there are only 2 really different ways of being a plant. You are either a herb or you are a tree. And maybe I can give you shrubs, but don't push me beyond that. Because of that, he's not only the founding father of botany, he's also the basal ancestor of all lumpers in ecology. And from him, all the way to the 20th and 21st century, there has been a very rich tradition of warp, of lumping ecology. Very general patterns of how to be a plant or an organism in general. These are just some prominent examples during the 20th century. And these general ideas have been tested empirically very many times, and increasingly so. Now, I do apologize if your paper is not here, or if your favorite paper is not here. The slide was getting really, really crowded. And the whole point of this is to illustrate that empirical work beyond single organs and beyond restricted floras is actually not that abundant. So we wanted to go for that critical gap. We wanted to identify general syndromes of plant specialization at the whole plant level and at the global scale. And we wanted to deal with all three functions of the Darwinian struggle for existence. So we wanted to deal with growth, survival and resource preemption, and reproduction in the Darwinian sense, so at the individual level. Now, to make this whole thing operational, we needed to identify a relatively small set of traits that would be fundamental enough to encapsulate together all these three dimensions, and at the same time available for a very large number of plants around the world. So after much thought, we settled for plant height, propagule mass, leaf mass per area, and nitrogen per mass, leaf area, and stem-specific density. Now, another great thing of being in this meeting is I don't have to explain the traits. If you're here, you either swear by them or you are an active militant against them. But the point is, these are fundamental enough to be at the core of plant responses to the environment and also effects on major ecosystem processes. Now, to build a database like this wouldn't have been possible even 5 years ago. This was only possible because of TRI, and again, I don't have to, probably for the first time, I don't have to advertise TRI, because you already know about it, because you knew already, or you heard Jens' great talk of yesterday. So thanks to TRI, we managed to put together a large data set comprising all biomes on Earth and just over 46,000 species around the world, belonging to more than 400 families, and including some of the most extreme plant traits known to science. Now, we don't claim to have covered the whole range of variation of these key traits in the planet, but we think we are reasonably close with the strain values. Now, with all this information, we wanted to construct the multidimensional trait space of vascular plants. We wanted to do this, the outer shell of that multidimensional space, and we also wanted to ask, within that, what is the actual volume? What is the form and the size of the volume actually occupied by vascular plants living today? So this is what we call the observed trait space, and we tested that space against a number of null models. And this is the observed space. This is the actual volume in trait space occupied by vascular plants that are living today on the planet. I can only show you 3 dimensions at a time, but in the paper we give a link to a Shiny app online, and there you can select any combination of 3 traits and look at the observed volume from very different angles and test it against a number of null models. The bottom line is that the observed trait space was significantly different from all the null models, strongly suggesting strong trade-offs and constraints on vascular plant design. But that, of course, was just the outer shell. We wanted to know the distribution of species within that shell. And for that, we did something extremely simple. We did a PCA of all those species for which we had empirically measured values for all 6 traits. And we found that 75% of the variation in multidimensional space was captured by just one plane. This plane, which we call the global spectrum of plant form and function. Now, Haydn probably made a much better work than I'm going to do in explaining it yesterday, but I will explain it anyway. Here, each point is not an individual. Each point is a species. It's a mean of many individuals, sometimes not so many. And the icons represent the higher and lower extremes of the traits. So, for example, this is very high nitrogen, very low nitrogen, huge leaves, tiny leaves, etc. One of the major axes of this plane, this axis, represents the size of whole plants and also plant organs goes from tiny plants with tiny leaves and seeds all the way to very tall plants with large leaves and seeds. And the second major axis this way is the leaf economic spectrum. Here you have robust, conservative, carbon-expensive leaves all the way to flimsy, fast-growing, short-lived leaves. Now, only two dimensions containing non-redundant information were axes 1 and 2. Now, the best way to imagine the global spectrum of plant form and function is not axis by axis separately, is to picture it in your mind like the galactic plane of the Milky Way. So if you think of the Milky Way, as you know, is slightly tilted. And although, of course, there are celestial bodies in more than 2 dimensions, the Milky Way is not a cloudy blob. Most of its biomass is strongly concentrated into a disk, into a galactic disk. In a similar way, a global spectrum of plant form and function is remarkably flat. Now because we are supposed to talk about the limits of trade space. So let me illustrate some of the plants in the fringes so you have a more intuitive way, image of what's there. In this trem, you have the Brazil nut all the way to Arabidopsis. I know that there are many, many different Arabidopsis, but they are all confined to, just to the limits of the galaxy, in a remote corner of the galaxy. Then this way you have tough leaves, slow-growing gymnosperms such as the monkey puzzle, all the way to flimsy submerged aquatics like Utricularia and Myriophyllum. Here the highly specialized Hackets, all the way to Datura, the devil's snares, which are plants which are very acquisitive, very fast-growing, very tender, but usually toxic, full of nitrogen. Here, the heathers, I think we are going to see some today, all the way to the sacred lotus. So now you have an idea of what's there. Now, what a true lamper would think when looking at this picture. I think the first thing she would think is, what would have Theophrastus say about this diagram? And I guess the first thing he would have said is, show me where are the herbs and the goodies. And here they are. And probably his second question would be, okay, tell me if there is any really fundamental, really general difference between the herbs and the goodies. And the answer we got at this global scale is yes and no. Yeah, on the one hand, we know that we can see here that herbaceous and woody plants occupy different regions of the global spectrum. Woody plants are offset on PCA1, and not surprisingly, they are taller, denser stems, bigger leaves, bigger seeds, and higher LMA. But at the same time, there are some very remarkable similarities. Goodies and herbs are strongly overlapped on the leaf tissue axis. And if you see the plot of the very fundamental variables in the global spectrum, in the leaf economic spectrum, so nitrogen per mass and LMA, you can see both woody and herbs align pretty much on the same curve. And in both groups, leaf area goes up with height, but leaf mass per area doesn't. Actually, in both groups, leaf area is pretty independent from both LMA and nitrogen mass at this scale. And at the same time, at any given plant height, woody species have higher LMA than herbaceous one. So basically, a leaf doesn't seem to care too much whether it's hanging high or low with respect to the ground, but they seem to notice whether they are hanging on a herbaceous or woody plant. So to go back to Theophrastus' questions, there are some fundamental similarities, particularly in leaf tissue quality, between woodies and herbs, suggesting some really bound fundamental trade-offs there. But at the same time, we do find some general differences which include but go beyond those already observed by Theophrastus 2,000 years ago. This is as far as growth forms are concerned. Now, let me show you something about very large taxonomic groups. I think this shows some interesting trends on how plants have been shifting in the functional space with evolution. You can see here that different big taxonomic groups do occupy different portions of the spectrum. Gymnosperms are confined to the lower right corner, and angiosperms occupy the whole functional space, including and going beyond that of gymnosperms. We think that aided by all their vascular innovations and leaf anatomy and physiology innovations, angiosperms have been able to explore areas of leaf side and acquisitiveness that are simply beyond the reach of the gymnosperms. Again, this is the plot of leaf nitrogen per mass and LMA. You can see most of the big groups of angiosperms align on more or less the same slope. The slope of gymnosperms is steeper. And within the major speciose families of angiosperms, again, they pretty much align on a similar slope. So again, there's something fundamental there. But we could go forever in this exciting bivariate relationship, but this is not, to me, the most exciting bit of our work. The most exciting bit to me is where the plants are in whole plant design. So where they are in the bidimensional spectrum. And here I would like you to concentrate on the color overlay. This color overlay is not to fry the eggs, as one of my co-authors say. It's actually a probability density map. So the whiter the color, the more rare the trait combination is, and the hotter the color, the more common the trait combination is. You can immediately see that most of the vascular plant diversity on the planet, not the biomass, the number of species, is actually lumped in two functional hotspots. One at the heart of the herbaceous space, and one within the woody space, slightly eccentric. Now, these functional hotspots are occupied by a very large number of very phylogenetically distinct families and orders, suggesting that these are successful trait constellations that have been achieved repeatedly during the evolution of vascular plants. We are quite excited about them, but I think equally interesting is these pale areas, these empty or half-empty areas. Of course, some of the areas in the spectrum are empty because of purely biomechanical reasons. You cannot really have a hugely tall tree with a really dense wood and hang from it an incredibly large and flimsy and nitrogen-rich leaf. It just wouldn't work. But we think that the constraint and lumpiness of the trait space is much higher than you would expect purely on the basis of biomechanically enforced trade-offs. We believe that here there's a hallmark of natural selection, and I don't have the time, but if I had, I would have liked to show you that you can also see the traces of unnatural selections by us. For example, we can think of these fringes, of these pale fringes, as not very popular combinations, as the front line, what plants are achieving now. Or you can think of it as the receding line, those who have been losing the evolutionary and selective battle for a while. There's no time now. Anyway, this we realize is an exercise in extreme lumping ecology. We have tried to encapsulate all the diversity of vascular plants in only 8 traits, 1 plane, 2 hotspots. One is your just usual herb you are going to have in your sandy walk. The other is just the archetypical tree you draw in the kindergarten. So extremely simple, extremely lumping. Probably Theophrastus would have liked it. So how does this relate to the much more nuanced functional ecology, to the many differences in which plants differ from each other and adapt to their biotic and abiotic environment? I think this all adds multidimensional depth, if you want, to this rather flat volume. So this is not incompatible with all the other more wafty ways of looking at plant traits. But I think the main strength, the main beauty, if you like, of this is precisely its simplicity. Here you can think of the global spectrum of plant form and function as the first global picture of essential whole plant functional diversity. And here you get an image of whole plant design, continuous, quantitative, and defined only by 2 coordinates. So we think that could be useful as a backdrop on which you can map plants and plant communities in the planet. Also, we think is interesting to understand, as we are trying to do now, the selective and evolutionary trajectories of plants in the past and also in the face of environmental change. And because it's computationally light, you have the whole plant with just 2 coordinates, sometimes I like to believe it could be useful somehow for dynamic vegetation models. But another advantage of being in this meeting is I don't have to just struggle thinking whether they would be useful or not for these dynamic models. The models are here, so you guys can tell me whether this, yes, is a really good idea and then this is the way to do it, or just forget it doesn't make any sense at all for our models. So I would like to conclude by saying that the global trait space of vascular plants is no blob. It's actually remarkably constrained and lumpy. The variation is largely concentrated in a plane that we call the global spectrum of plant form and function. Both size and leaf tissue aspects are essential and enough at this coarse level. The spectrum is strongly granular. Some trait combinations appear to be much more popular than others across the phylogeny. The spectrum provides a number of possible applications. I already described them. And finally, a reflection from our work. We found very, very strong hints of coordination of traits at the whole plant level, which strongly suggest that rather than going for services of disembodied traits, a much more fruitful way to go is to consider the whole phenotypes. And I conclude with a big thank to all the colleagues in this work. It really wouldn't have been such exciting and such more fun without their strong involvement. Thank you very much.